This was prepared by the DC-6 section of the Flight Training Center, United Airlines. Propellers are a coupling device which change engine power into thrust. In the DC-6 type aircraft, the thrust or pull of the propeller is applied to a thrust-bearing assembly in the front section of the engine. The engine then, through the engine mounts, pulls the aircraft. This is a Hamilton hydromatic constant speed propeller assembly used on all DC-6 aircraft. It incorporates full feathering and reverse thrust features. The propeller, rotating at 0.45 engine speed, changes the rotary motion of the engine to thrust. With engines turning at 20 revolutions, propellers turn 9. At a given power setting, the propeller controls the speed of the engine by loading, which is done by changing the prop blade pitch angle so the propeller can utilize the same engine power as airspeeds vary. The engine is maintained at a constant RPM, indicated on the tachometer, by the propeller governor. The normal governing range is from the low pitch position of 30 degrees to the high pitch position of approximately 65 degrees. The low pitch position has a mechanical stop which, when displaced, permits the propeller blade angle to be set to a -8 degrees. Degree pitch blade angle is used to develop reverse thrust, which thrust is used only on the ground to slow the aircraft after landing. At the other end of the blade pitch angle range is the full feathered position of 96 degrees. Whenever the propeller blades are rotating, whether by engine power or windmilling, aerodynamic and centrifugal forces tend to move the prop blades toward the zero pitch, maximum RPM position. The propeller operating range extends from the full feathered position of 96 degrees to the reverse position of -8 degrees. There are micro switches located on the number 1 blade and the number 2 blade of each propeller, which terminates the unreverse function and cause an amber light in the cockpit to illuminate. When an amber reverse light illuminates, it indicates that the particular propeller is out of the normal governing range and is going toward the reverse thrust range. During feathering and unreversing, a motor-driven feather pump is activated. During unfeathering, reversing, and reverse holding, the feather pump plus a governor solenoid and solenoid valve are utilized. In the normal governing range, blade pitch angles, which are controlled hydromechanically with engine oil by the propeller governor, vary whenever RPM, engine power, and or airspeeds vary. Each engine has a governor which controls the engine RPM by setting the propeller blade angle. For example, increasing the blade angle causes the engine to slow down because there is more load on the engine. The speed reference in the governor is a set of engine-driven centrifugal flyweights, which are opposed by a speeder spring. In this case, the centrifugal forces of the flyweights are exactly counterbalanced by the speeder spring, and the engine is operating at the RPM desired by the governor. The governor uses oil from the engine oil pressure system. If the RPM is higher than that desired by the propeller governor, the flyweights compress the speeder spring. This action ports oil into the propeller dome to increase the blade angle. This places more load on the engine and causes it to decrease speed to the desired RPM. Should the engine RPM be less than that required by the governor, the centrifugal flyweights will be forced inward by the speeder spring. This action ports oil into the propeller dome to decrease the pitch angle of the propeller blades, which creates less load on the engine and results in engine speedup. Thus, the operating RPM of the engine is determined by the relation of the flyweights and the speeder spring. The propeller governor is mounted at the 10 o'clock position on the front case of the engine when viewed from the front. The governor governs the speed of the engine by setting the blade pitch angle to maintain a constant engine RPM. Changing the speeder spring tension will cause the engine RPM to change. Speeder spring tension is electrically controlled by the step motor on the head of the prop governor. There are three means of operating this step motor from the cockpit. 1. The toggle switches. 2. The master lever. And 3. The automatic synchronization. These controls are on the prop control panel on the pedestal. Governor RPM normally is controlled by the master lever. However, the toggle switches are the most reliable means of RPM control. They must be checked prior to every originating flight. The toggle switches operate independently of one another, and RPM can be changed in opposite directions on different engines at the same time. Toggle switch operation will override any other RPM governing control. All toggles are protected by one prop manual circuit breaker and have other mechanisms in common. Therefore, it is possible for all toggle systems to fail simultaneously. At the upper left corner of the propeller control panel is the master control lever, or master lever, which can change the RPM of all four engines simultaneously in the same amount. The selector switch must be in the Auto 2 or Auto 3 position for the master lever to be operative. The master lever also has a calibrate function. When it is placed in the full forward or full increase RPM position, the governors will be set to full takeoff RPM. Automatic synchronization is not operative when the master lever is in the calibrate position. Any engine may be toggled to a lower RPM when the master lever is in the calibrate position, and it will not return to takeoff RPM when the toggle is released. Automatic synchronization is not operative while an RPM change is taking place, but should resume its function as soon as the change has been completed. Any one of the toggle switches can override the master lever, even while an RPM change is taking place. The master lever operates through a follow-up system. When the master lever is moved, it mechanically offsets the follow-up system. The electrical mechanism which sends signals to the four governors recenters the follow-up system, so the master system stops when the RPM change has occurred. Noise level and vibration can be greatly reduced by keeping all four engines rotating exactly the same RPM. Within certain limits, an automatic synchronization system performs this function. The master engine selector switch is used for selecting either number 2 or number 3 engine as the reference, or master engine for automatic synchronization. For example, if the number 2 engine has been selected as the master engine, the RPMs of the 3 remaining engines, known as slave engines, are made to operate at the master engine RPM. When the master engine selector switch is in the center or manual position, both the master lever and synchronization system are deactivated. signals from the tachometer generator on each engine are used both for tachometer indications and synchronization. This is an example of perfect synchronization. It appears that the master engine has feathered, and then the other three engines were kept in synchronization to the feathered position. Could this actually happen? The answer is no, unless all four feather buttons were pushed. The synchronization system incorporates a safety feature that prevents the slave engine from following the master engine a dangerous amount. This safety feature is the limited band mechanism, which allows a slave engine to follow a master engine RPM approximately 3%. The resynchronize button is located at the left aft corner of the prop control panel. Pressing and releasing this button releases and resets the limited band mechanism and allows the RPM of each slave engine to change toward the master engine RPM. Noise level and vibration can be greatly reduced by keeping all four engines rotating exactly the same RPM. Within certain limits, an automatic synchronization system performs this function. When the number 1 and or number 3 throttles are in the takeoff position and a blue RPM limit light is out, the takeoff warning horn will sound intermittently. It will sound only when the aircraft is on the ground. The takeoff warning horn can be silenced by pushing this takeoff and cabin low pressure warning cutout button on the overhead panel, after which the takeoff warning horn system is automatically ready to sound another alarm. It will sound if another prop is toggled or if a different system takeoff warning alarm is generated. We have discussed prop control in the normal governing or constant speed range. It is possible to decrease blade angle below normal governing range for reverse thrust on landing or above the normal governing range to the feathered position to stop engine rotation in flight. Operation of the prop outside the normal governing range is accomplished by a high pressure oil from the electrical feather pump in the aft part of the engine. The high pressure oil is directed through the prop governor to the prop dome by the prop governor solenoid. The prop governor solenoid is normally de-energized, and high pressure from the feather pump moves the prop blades toward feather. When the prop governor solenoid is energized, high pressure oil moves the prop blades toward reverse pitch. Whenever the feather pump operates, high pressure oil is forced through the governor and the prop dome and then to the engine. Whenever the engine is rotating, the engine-driven scavenger pumps remove the oil from the prop dome and return it to the tank. For this reason, a feather pump should never be operated in an engine which is not rotating. Propeller feathering streamlines the prop blades so engine rotation can be stopped in flight and is a part of the in-flight engine shutdown procedure. The feather position is attained by extending the propeller operating range through high pitch to the 96-degree blade angle. With an unfeathered propeller, as shown above, air movement will cause the propeller to rotate the dead engine. This windmilling is highly undesirable, especially if the engine has had an internal failure. With a propeller feathered, as shown below, engine rotation is stopped, and there is minimum drag. When one of these red guarded feather buttons, located on the forward overhead panel, is depressed, the feather pump is electrically energized to furnish high pressure oil to the governor, which drives the propeller blades beyond the normal range of 96 degrees, or feathered position. In each oil tank, the last 2.5 gallons is reserved for feather pump operation. The firewall shutoff valve does not shut off the feather pump operation or oil flow. Each feather button circuit is protected by a feather control circuit breaker on the MJB. The circuit to the feather pumps is protected by a 500 amp circuit limiter on the MJB. When a feather button is pushed in, it is automatically held there by a solenoid. After 15 seconds, the feather button pops back to neutral. Normally, only about 7 seconds are required to feather a propeller. So, 15 seconds of feather pump operation is more than enough. After the feather pump has stopped, the prop should remain feathered. A propeller may be unfeathered by pulling and holding out the feather button. The button returns to the neutral or off position. When the feather button is held out, the feather pump relay starts the feather pump. High pressure oil from the feather pump is directed by the prop governor solenoid, which is energized, to move the blades out of the feathered position toward the normal governing range. If the aircraft is in flight, as soon as the blades move from the feathered position, the prop begins to rotate and accelerate. Reverse thrust blade angle enables engine thrust to be used for de-acceleration. This function is used only on the ground. The prop blades are moved to a -8 degree angle, but the direction of engine rotation remains the same. Reversing of the prop blades is accomplished after landing by pulling the throttles aft into the reversed range. Before the throttles can be moved into the reversed range, a mechanical lock, called the Martin bar, shown here being unlocked by the captain, must be activated. Now that the Martin bar has been unlocked, the throttles can be moved from the forward idle position into the reverse range. The amber lights illuminate as the prop blades move toward reverse past the 15 degree position. The prop blades continue to the -8 degree position and remain there as fixed pitch props as long as the throttles remain anywhere in the reverse range. The further aft the captain pulls the throttles, the more power is applied to the engines, and the more reverse thrust is produced. There are 2 switches located under each throttle. One is called the reverse switch. The other one is the safety switch. When the throttles are moved into the reverse range, these reverse and safety switches are closed. Closing these switches by throttle action energizes the feather pump relay and the prop governor solenoid, sending high pressure oil through the governor, moving the prop toward reverse. This is essentially the same operation as unfeathering. During normal governing operation, mechanical low-pitch stops block movement of the piston in the prop dome at the 30 degree position. This is a safety device to prevent high overspeeds if the prop governor fails. These low-pitch stops are removed by a high-pressure oil from the feather pump when the pump governor solenoid is energized, as is the case when the throttles are moved into the reverse range. Once the low-pitch stops are removed, the piston can continue to move the propeller blades all the way to the -8 degree reverse thrust position. The prop blades are brought out of the reverse thrust position by advancing the throttles into the forward thrust range. Moving any throttle back into the forward thrust range relocks the Martin bar. Since several forces tend to prevent the prop blades from returning to the normal governing range, the feather pump continues to operate with the prop governor solenoid de-energized. This high-pressure oil moves the blades toward the feather position. When the blades reach the normal governing range and above the low-pitch stops, a cam-operated switch on the number 1 blade shuts off the feather pump. Whenever the feather pump is operating, whether it is during feathering, unfeathering, reversing, or unreversing, the prop de-icer for that propeller is automatically cut off. This is done because both the feather pump and the prop de-icer draw heavy current through the same line. When the feather pump has been shut off, normal de-icing will resume, even on a feathered prop. The propeller system has been covered in some detail. If there are any questions, your instructor will be glad to explain them. This concludes the DC-6 prop presentation.